Hello there, everyone. Thank you for joining me today in this lesson about estimating the area under a curve. We have two objectives for this lesson today. We are going to explore accumulations of change, and we are going to approximate the area under a curve using a Riemann sum. So let's first talk about how area fits into this calculus class and how it relates to what we've been studying for most of the year so far, right? So here's a little warm-up exercise. A holiday traveler drove for 3 hours with the cruise control set to 55 miles per hour. The traveler's velocity graph is then shown to the right. You can see it's constantly 55, constant speed, 55 miles per hour. Let's find the area between the velocity curve and the x-axis, right? That's the red shaded rectangle. And then we're going to talk about what that area represents. What does that number represent regarding this person's travel? Okay, so let's find that area here. We've got ourselves a rectangle, so we'll take the base times the height, where the base of this rectangle is 3, right? And the height of this rectangle is that 55. Well, 3 times 55 gives us a total of 165. But what does that number represent in regards to this person's travel? Well, think about what we did. We took 3 times 55, where 3 was the duration of the travel, the time, if you will. 55 was the rate of change of this person's position, 55 miles per hour. And when you take time times rate, you get the total distance traveled, the displacement, if you will. So 165, the area between the velocity curve and the x-axis, represents the distance traveled by this individual, sometimes called the displacement. Right? I'm going to make this connection more formal here in a little bit, but that's a good warm-up into kind of understanding how area fits into this calculus class. So let's hit that more head-on here. Let's connect everything we did in semester 1 to what the big ideas are from semester 2. In semester 1, we focus most of our study on rates of change, derivatives, applications, etc. Well, here in semester 2, we focus on how those rates of change accumulate over time. The big idea being that if a curve represents a rate of change, like the velocity curve in the last example, then the area between that curve and the x-axis represents the accumulation of that change over time. The example we had was the area under a velocity curve, and that gave us the distance traveled or the displacement. Right? There are other examples too. If we've got a curve that describes the rate of change in a population, the area under that curve will give us the total population then, the accumulation of all of that change over time. Okay, so our lesson today being about finding the area under a curve, okay? And that problem can be either a geometry problem or a calculus problem. On the left-hand side, this velocity curve is made up of, some linear functions here, such that we could calculate the area trapped underneath that curve using basic geometry formulas. We have a couple triangles there, a couple rectangles. We wouldn't really need calculus in order to, find that area. But then what happens when our curve is not made up of linear functions, right? Like this curve here, we don't have a specific geometry formula that could help us encapsulate this area here. So we're going to learn precise calculus techniques later for that situation, but for now, the best we're going to do today is we're going to estimate that area using geometry formulas we already know. So here's an example of a curve, looks to be a parabola perhaps, right? We could estimate the area trapped under that curve by trying to split that area using a bunch of rectangles. Because we can find the area of a rectangle using base times height, we could then add all those rectangles together to get a decent estimate. So today we are going to start with some rectangular approximations. In other words, to find the area under a curve, we're going to split that area into a bunch of rectangles, add up the areas of those individual rectangles. We're not going to focus so much on this example here in our lesson. That's a geometry problem. Split the area into geometry shapes you already know, whose areas you can calculate precisely. We're going to focus more on these today. And there are 3 rectangular approximation methods we're going to use. We're going to use the left Riemann sum, the middle Riemann sum, and the right Riemann sum, sometimes referred to as LRAM, the left endpoint rectangular approximation method, MRAM for midpoint approximation, and RRAM for the right endpoint approximation. Right? And these images kind of show the differences between the two. LRAM, MRAM, and RRAM, those techniques tell us how we're going to find the heights of these rectangles. Are they dictated by the left endpoint of each rectangle, the midpoint of each rectangle, the right endpoint of each rectangle? That's the difference between these three approximation techniques. Let's start with an LRAM example. Let's use the left endpoint rectangular approximation to estimate the area under y equals negative x squared plus 6 on the interval from 0 to 2, and we're told to use 4 rectangles. So we're going to take this curve, fill it in as best we can with 4 rectangles, add the areas of those rectangles to get an approximation of the area under this curve. Well, to find the areas of our rectangles, we got to know the base of our rectangles and the heights of our individual rectangles. And let's start with the base. To figure out how wide our rectangles are, to figure out the length of the base, we've got to consider the interval that goes from 0 to 2 and the number of rectangles, 4. So our interval, if you calculate the length of it, b minus a would be 2 minus 0, and we're going to split that into 4 rectangles. So really, to find the base of our rectangles, we can do this exact calculation. We can find the distance between our endpoints, 2 minus 0 in this case, and divide by the number of rectangles we're going to use. That's 2 divided by 4 here, that's 1/2. So each of our rectangles will be half of a unit wide. The base of all of our rectangles will be consistently 1/2. And I've gone ahead and I've made sure that the scale on my graph kind of fits that well, right? So rectangle number 1 is going to span this interval, rectangle number 2 this interval, and so on. Now we need to draw in our rectangles and find the heights. And we've got to pay close attention to the fact that we are doing a left endpoint rectangular approximation. So if I consider rectangle number 1, which is going to kind of fill in this column of space here, the height of this rectangle is dictated at the left endpoint of this interval. So my interval spanning from 0 to 0.5, the height is going to be dictated over here at the left endpoint. So if I go to that left endpoint, go all the way up to my curve, here is the height of my first rectangle. I'm going to sketch in that rectangle in orange. This is it. For the next rectangle that spans the interval from 0.5 to 1, again, we go over to the left endpoint of that interval, go all the way up until we see where the curve is at for a y value at that endpoint. There's the height of our second rectangle. And we're going to calculate these exact heights in a moment. Right now, I'm just drawing in the rectangles. Okay, speeding up a little bit here now. Here's the height of our third rectangle, dictated by, again, the left endpoint of that sub-interval. Finally, our fourth rectangle, here's that left endpoint. Here's the height of our fourth rectangle. I'll shade these in a little bit, perhaps. These are the 4 rectangles we are going to use to approximate the area under this curve. Now, clearly, we're going to get an overestimate because these rectangles extend above that curve. We're going to talk more about that in subsequent lessons and in your homework assignment. So those are our rectangles. Let's now calculate the area of each, and we can add them all up in order to approximate this area. So we're going to need the heights of our rectangles. In blue here, I'm going to go ahead and create kind of a mini XY table of values, where our X values are those left endpoints. Those were 0, 0.5, 1, and 1.5. The Y values are going to give us our heights, and we're going to get our Y values like we normally do. Take our X's and plug them in. So if we plug 0 in for x there, we'll get 6. I'm going to speed up a little bit here because if I go through all of these calculations, it'll make for a pretty long video. And it's probably going to be long enough the way it is. So those are the corresponding y values we get. Those are the heights of our rectangles for the given left endpoints that we used. So now to get our left endpoint approximation, we're going to go ahead and add up the areas of all these rectangles. Now let's think about this for a moment. We can do a few things to speed this up. For each of our rectangles, we've got base times height, base times height, base times height, base times height. But if you think about it, the base of each of our rectangles is the same. It's consistently 0.5. So we could take that base and we could go ahead and we could factor it out. because it's the same. That b is the same across all of those individual calculations. Now, we don't have to do this, but this is one thing we can do to speed it up a little bit. Now, we do have to add up all of the heights, though. We factored out the b, right? Base times height, base times height, base times height, base times height. The base was 0.5. We factored it out. But we do have to add up all the heights. We've got to add up 6, 5.75, 5, and 3.75. And when we add those up and multiply by 0.5, we end up with an approximation of 10.25, 10 1/4, if you will. Remember, that's an overestimate. I can tell that based on, I can see the rectangles extend beyond that curve. That won't always be the case for LRAM. You'll explore that a little bit in the homework assignment associated with this. Let's use the same curve and let's do a right endpoint approximation. Let's speed things up a little bit though, right? Same curve, same interval, same number of rectangles. So the base of our rectangles are still going to be half of a unit, right? So same width there, okay? But when we draw out our rectangles, they're gonna look slightly different here. So our first rectangle spans this interval, right? But this time we're doing a right endpoint approximation. So if I go to the right endpoint of that interval and I track it all the way up to where the curve exists at that endpoint, this is now the height of our first rectangle. You can see it's actually below the curve. And if I do that for the rest of my subintervals, going to the right endpoint, tracking it all the way up to where the curve exists as a y value there, you can see that this time we're going to get an underestimate of the true area. Our rectangles fall short of the actual height of the curve. There's a certain characteristic of this curve that dictates that. Again, you're going to explore that more in your homework. We need the heights of each of our rectangles here. So just like before, we make a good old-fashioned table of x, y values. But let's slow down a little bit here. We're not going to start at 0. We're using our right endpoints now. Those are 0.5, 1, 1.5, and 2. Those are the x values we would have to plug in to get our corresponding heights. I'm not going to go through all of those calculations, of course. That would be very dry. And make this longer than it needs to be. Some of these we already did calculate, right? So that could help speed things up if you had a situation like this where we're using the same curve but a different approximation. Here's a new one that we didn't have to calculate before. So let's get our right endpoint approximation now. Again, we can factor out that base because it's constant across all of these calculations. It's 1/2, but we do have to add up those heights, 5.75, 5, 3.75, and 2. And when we add all those up and multiply by 0.5, we get 8.25. Makes sense that we got a smaller answer here because, again, we know this is an underestimate. We can tell that from our picture there. So far we've had an overestimate, an underestimate. Okay, let's see how the midpoint approximation looks like it will stack up. All right. So here again, same curve, same interval, same number of rectangles. That speeds things up for us. The length of our rectangles, the base, if you will, is again 0.5. Okay, but this time our heights will be dictated by the midpoints for a midpoint approximation. So my first subinterval spans from 0 to 0.5. The midpoint there would be 0.25. And if I kind of track that all the way up to find the height of that first rectangle, it's going to be somewhere right in here. Not a perfect sketch, but you kind of get what I'm going for here. The midpoint of our next subinterval would be 0.75. And if I track that all the way up to see what y value we have, here's the height of our second rectangle. Our next midpoint of our next subinterval would be 1.25. So here's an estimate of where that height would be. Finally, the midpoint of our last subinterval would be 1.75. And you can see that we do have our rectangles that are, partially above, partially below the curve. And so you might think we're going to get an exact approximation here, but that's not quite the case. Not for this type of function anyway. I won't say any more about that right now. Okay, the base of all our rectangles is 0.5. We know that, but we need the heights of our rectangles. Okay, take care this time. The numbers we plug in are the midpoints of our intervals. 0.25, 0.75, 1.25, 1.75. And that makes the calculations a little bit more messy here. Maybe we would have a calculator for this problem perhaps to speed things up. These are the x values that we have to plug in to get the heights of our rectangles. Okay, again, we're plugging them in here, squaring them, multiplying by -1, adding 6 to them. All right, these are a little bit more messy. I'm not going to read off every single digit because that becomes very obnoxious very fast. I'm not rounding to 3 decimals here. These end quite nicely after 4, so I'm just going to use all of those to get the most accurate answer possible. So here we go now. Let's get our approximation for our midpoint rectangular approximation method. Once again, we can factor out the b because it's the same base times height, base times height, base times height, base times height. But the heights are all different. We're going to add up all of the heights up above. Okay, and I'm going to speed up this video. I'm not going to write all those down, but we would add up all of those there, multiply by 0.5, and get this answer here, which is between the left approximation and the right approximation, in this case, 9.375. Again, not exact. Looks like it could potentially be. Not always the case. Would be the case for linear functions, but not here. So, at this point, we have done left, right, and midpoint approximations to approximate the area under a curve. You may have been wondering, maybe not, okay, is there anything we can do to get a better estimate, right? We know that we're going to learn precise calculus techniques later on where we can get the exact area, but for the time being, is there anything we can do to improve our estimate? Well, there's a few ways we could do that, okay? If we used more rectangles, we would get a better approximation. More rectangles would be able to fill in the space more precisely, right? More and more rectangles would get a better and better approximation. We're going to talk more about that later in this chapter. One other way that we could improve our estimate, though, is to not necessarily use rectangles, but use a different geometric shape whose area we can find precisely. And you see that shape here. Instead of filling in this area using rectangles, this image has this area filled in with a series of trapezoids. Here's one such example. These trapezoids have a height and a couple bases. And remember that we find the area of a trapezoid by taking the height, cutting it in half, and finding the sum of the bases. You can see how that can result in perhaps a better approximation because we don't have quite as much missing area that we get, or an overestimate that we get with rectangles. So this leads us to our final idea for this video today, the trapezoidal approximation method. Okay, so here's a different curve. Recognize that. We're going to estimate the area under this curve on the interval from 0 to 4. This time we're going to use trapezoids, and we're going to use 4 of them, 4 sub-intervals. In order to find the areas of all these trapezoids, we're going to have to know the heights. We're going to have to know the bases of each. Let's start with the heights. Okay, how wide are the trapezoids here? These trapezoids are kind of rotated 90 degrees, right? Where their heights are actually these distances down here. Well, let's take a look. We're spanning the interval from 4 to 0, right? So we find the length of that interval. And then we divide by the number of trapezoids we're going to use. We're going to use 4 trapezoids. So each of our trapezoids is 1 unit wide. That's technically the height of our trapezoids. So our first trapezoid will span this subinterval. Here's trapezoid number 2, trapezoid number 3, trapezoid number 4. Let's go ahead and sketch those in. Here is our first trapezoid. These are the bases technically, right? And then I'm going to connect those endpoints there. Here's trapezoid number 2. Pretty rough sketch here, but that's all right. Here's trapezoid number 3. Looks like we might have a little bit of symmetry we can appeal to here. Here's trapezoid number 4. Now it does look like we're going to get an underestimate here because we have these little slivers up top that we're missing. You're going to explore that a little bit more. When does trapezoidal approximation result in underestimates and overestimates? You'll explore that a little bit in the homework assignment that goes with this. So let's find the area of all 4 trapezoids, add it up to get an approximation of the area under this curve. Okay. We know the heights of all of our trapezoids is 1. We need the bases. Okay, so again, I'm going to make a little XY table of values here. And if look at all the bases we've got to calculate. We've got to calculate this one here, this one here, this one here, right? Perhaps we can appeal to the symmetry of this situation to speed things up a little bit though. So the first x value we have to plug in is 0, okay? And then 1, 2, 3, and finally all the way up to 4 there. We're going to plug those x values in where we normally would to get corresponding y values. I'm not going to talk through that calculation because you can do that calculation, but these are the corresponding y values we get, and we do have the symmetry we expected. So let's lay out our trapezoidal calculation now. I like to use TRAP to approximate this. The area of a trapezoid is found by taking the height, dividing it by 2, and multiplying by the sum of the bases. Well, let's look at our first trapezoid here. This base is 2 units, this base is 5 units, so I would have 2 plus 5 in these parentheses here. That's the area of trapezoid number 1. Here's the area of trapezoid number 2. That's the height divided by 2, 1 divided by 2. Okay, the left side of that, this base is 5. This one was 6 units, so we would have 5 plus 6. Here comes trapezoid number 3 now. This is height cut in half. We would have 6 and 5 as our 2 bases there. Finally, here's the area of trapezoid number 4, where the bases are 5 units, and this one was 2. Now, there are opportunities to speed things up here a little bit as well. If you look at what we have, we've got this 1/2 in each of our little mini calculations that we could factor out, just like we factored out the base when we were doing our rectangular approximations. So that's one step we can take to speed this up a little bit. But if you look a little bit further, when we factor that out, we would have 2 plus 5, plus 5 plus 6, plus 6 plus 5, right? And so if you look at, we're going to use this base twice. There's 2 of them. And so what we could do here is we could take this 2, but then we've got 2 of these exact same number. So we could say 5 plus 5 if we wanted to, but we could also just double 5, right? And we could do the same thing with 6 here. There's 2 of those being added together. Does it speed things up tremendously? Probably not, but I still want to point that out. Here, this number 5 would be added up twice. So again, we can do 2 times 5. Finally, this number here, there's only one of them on the end. We had some symmetry, but that won't always be the case. So don't count on that, okay? But you can count on this type of situation here. So we run the numbers, we add all these things up, multiply by the 1/2 we factored out, we get 18 for that trapezoidal approximation. So is our estimate an overestimate or underestimate of the true area? We already talked about that here. We're missing these slivers up top. Okay, so this is going to give us an underestimate. Why do you suppose that is? I don't want to spoil that here because I want you to think about it and then investigate that a little bit more in the homework assignment that is associated with this. There's a certain characteristic this curve has that means we're going to get an underestimate from these trapezoids. Maybe you could draw a picture of something that would give an overestimate and then compare to see what that characteristic is. Longer lesson today, tough one to do with the video. I appreciate you sticking it out. Today we started by talking about how area is relevant for us here in this calculus class, how it connects to those rates of change we learned about in the first semester, and finally we practiced approximating the area under a curve by using both rectangles and trapezoids. Remember that I did not focus on examples like this one here, where we could split our area into specific geometric shapes. You'll see some of that on your homework, triangles, rectangles, perhaps semicircles. You'll see some of that. I wanted to focus on our approximation methods here. So that's it for lesson 6.1 to 6.2. Thank you for watching.